Up to corrupted file. This file seems broken, or is it? Maybe a couple of bytes could make all the difference. Can you figure out how to bring it back to life? So this is what we did for corrupted file challenge. The first thing that we did was we checked the file using file command. It returned generic data indicating a missing or corrupted file header. We inspected the hex dump of the first few lines using xxt file pipe head-n5, which prints the first 5 lines. We observed the string jfif in the ASCII column, confirming the original file type was probably a JPEG image. We identified the corrupted starting bytes at offset with 5C78FFEO. Standard JPEGs must begin with FFD8 FFEO. So we ran hex editor file to change characters, and we then opened the flag.jpg and revealed the image for the flag. DISKO 1. Can you find the flag in this disk image? So here are the notes from the challenge that we just did. We had a .gz file, which is a single file compressed format commonly used in Linux. It shrinks file sizes for easier downloading, but must be decompressed before use. It was also a .dd file, a raw bit-by-bit copy of a storage drive, containing all file systems, files, and even deleted data in unallocated space. To decompress, we wrote gunzip file.dd.gz, and then to search for the flag, we just ran string file.dd grep-i pico. Strings extracts the readable text sequence from the raw binary data. The pipe passes the text directly to the next command. grep-i search for keywords, ignoring case sensitivity. Moving on to SSTI1, web exploitation. I made a cool website where you can announce whatever you want. Try it out. This challenge involved server-side template injection. Web developers use template engines to build dynamic web pages. An SSTI vulnerability happens when the web app takes raw text typed by a user and directly pastes it into the template engine's code instead of treating it as safe data. Because of this, the server gets confused and executes the user's input as if it were a command. What I'm going to do is I'm probably going to create a theory video on server-side template injection with all the different commands that we could use, the processes of how to go about it. But for now, I'm just going to give the gist of what we did, because this deserves a video on its own, a good 30 to 60 minute, even longer, multiple series video. So what we did in this challenge is we found the echo point. We spotted an announcement box that printed back exactly whatever we typed onto the screen. First we did the math test. We typed 7 times 7 into the box. If the website was safe, it would have just printed exactly what we typed. However, it instead printed 49, which proved the backend server was running our math-like code. We used a specific command to make the template engine print out its internal Python brain. This let us see what tools the server had access to. We then ran a command to list the files in the server's folders and spotted a file simply named flag. We then told the server to open that file and read the text inside of it, which printed the final flag to the screen. Think of it like ordering a cake with a custom message. You tell the baker to write a recipe instruction like, drop the cake on the floor. If the baker blindly follows the instructions instead of just writing it down, that's template injection. Pie time. Can you try to get the flag? Beware, we have pie. Here are the theory notes from the challenge that we just did. PI stands for Position Independent Executables. The quick gist. PI is a modern security defense built into applications. Normally, computer programs store functions like hidden win functions that contain the flag at exact predictable street addresses in memory. PI changes this by completely randomizing where the program sits in memory every single time it's booted up. It is the application equivalent of moving houses to a completely random neighborhood every morning. What happened in this challenge? The program's clue, the leak. When we connect to the server, the program printed out its current randomized location for the main function. The fixed distance trick. Even though the entire program moves to a random spot on every run, the distance between functions inside the program never changes. By looking at the program, we used a tool called objdump. We found the fixed blueprint layout. Main was always at position 0x133D. Win was always at position 0x12A7. Doing the simple hex math, we discovered that the win function lives exactly 0 times 96 bytes behind main. When the connection restarted, the server scrambled the addresses to a completely new location. I was trying to reuse an old address, and this caused a crash segfault because that old memory space didn't exist anymore. The solution. We realized we had to grab the live address from the active session, calculate 0 times 96 bytes backwards from it, which clearly meant changing the last 3 digits of the leaked address from 33D to 287, and send it back to force a jump directly into the winning code. Analogy. Imagine a luxury cruise ship. The ship drops an anchor in a completely different random port every single day. You can't tell someone, meet me at the corners of the ship from yesterday, because the ship moved. However, no matter what country the ship docks in, the captain's quarters is always exactly 96 steps down the hole from the main deck. As long as you know where the main deck is today, you can find the captain's quarters. So, final clarification. Pi changes the total position of where programs are in memory, but the actual processes like win and main stay the same fixed distance relative to each other. I hope that makes sense. I'm definitely going to make a theory video on this. This is a pretty good challenge. Head dump, web exploitation. Welcome to the challenge. In this challenge, you will explore a web application and find an endpoint that exposes a file containing a hidden flag. The application is a simple blog website where you can read articles about various topics, including an article about API documentation. Your goal is to explore the application and find the endpoint that generates files holding the server's memory, where a secret flag is hidden. So these are the notes for this challenge that we did today. The challenge combined two completely different web security concepts: HTTP request methods and memory dumps. When you browse the web normally, your browser asks for web pages using a method called get. However, you can also use a hidden method called head, which asks the server to send only the behind-the-scenes data while hiding the actual page content. If developers leave advanced debugging or system diagnostic features turned on, an attacker can trick the system into exporting a heap dump, a literal copy of the server's live memory RAM where active flags or passwords might be temporarily floating around. What happened in the challenge? Well, by reading the article on the Target blog about API documentation, we found an exposed Swagger user interface page. This page acted like a blueprint map revealing a hidden diagnostic route, get/heap dump. Because the challenge was called head dump, we used curl-I in our terminal to query the endpoint using the HTTP head method. This let us inspect the server's response headers to see if a flag was sneaked directly into the metadata. The server response headers showed a content disposition attachment for a massive 11 megabyte file named heap dump heap snapshot. This confirmed that visiting this route forces the server to create a raw file containing a snapshot of its entire live memory. We downloaded the full memory dump using curl. As you can see here, curl at the website -o memory.heap snapshot. So -o stands for output, and without it, curl will try to dump the entire file immediately into the terminal. So the -o creates that separate document for us so that it doesn't look really messy and clunky. Since the snapshot contained thousands of lines of raw system strings, we piped the output into strings and grep to cleanly filter through the noise and pull the text format of the hidden flag out of the server's RAM layout. So you can see here, strings memory.heapshot, which is the file that we saved it as, pipe grep -i is ignore case sensitivity, and we did pico, as we know flags from picoctf start with pico. That was that challenge. I'll definitely do a theory video on server-side template injection, as well as I'll do a theory video, an example video on position independent executable. And I will probably also do a video on web exploitation. Maybe if you guys comment, I might do a video on that. But I feel like the more web exploitation challenges we do, the better we'll get at it. Anyway, it's been 2 hours. Thank you very much if you've watched, and I will see you tomorrow.